section 4.2, and we're looking at resultant moments here, and we hinted at this at the end of section 4.1. We've got a diagram that looks like this. Now, when you see a diagram that looks like this, it's very tempting to think about it as a seesaw, right? So there's a seesaw which for some reason somebody's put the pivot here, and it can be pushed down on this side or up on this side. It can be pushed down on this side or up on this side. And what's happening in this case is that something's pushing it down here, something's pushing it up here, and something's pushing it up here. Now that's a perfectly reasonable way to think about it. The problem with that is that if that's happening, then the weight of the seesaw automatically pushes downwards. And in these questions on this exercise, I could draw this diagram and not put a downwards force on it. And if this was a seesaw, then this is down and this is up, then of course there has to be a weight of the seesaw pulling down. So it might be helpful in this exercise to continue thinking of this as something flat that we're looking at from above, and there is a pivot point here, and we're pushing around this pad of paper by somebody's pushing down there that way, somebody's pushing here upwards that way, and somebody's pushing here upwards that way, and we want to know what actually happens. Does the paper start going this way or this way? So it might be helpful to keep thinking about it that way. On the other hand, we're going to get into so many questions where there is a seesaw and people standing on the seesaw, or a beam and people standing on the beam, that maybe starting to think about these as seesaws is reasonable. Both of those are a good mental picture to have in your head of what's going on here, okay? So what do we have? We have 2 meters here. We have that all of these forces are at 90 degrees. We have 1 meter here. We have 1 meter here. We have 3 newtons, 4 newtons, and 5 newtons. The way we're going to deal with this is we're going to just think clockwise moments and anti-clockwise moments, and we want to know the resultant moment. So clockwise, well, each of the forces involved is going to provide a turning force in one direction. Sometimes people find it difficult to picture which way is this turning. So let's pick one force and let's think about it. I'm going to put my pen on there and say that I've fixed this piece of paper there. If I'm pushing here, what's going to happen to this piece of paper? Well, it's going to turn that way. Which way was that? We're turning, it was turning that way. That's anti-clockwise. So the anti-clockwise moments, this one is 1 times 3, and I'll put a little tick next to that because I've dealt with that one. Put my finger on there, keep that still, and push in the direction of that 4 Newton force. Which way is this paper moving? It's turning that way, which is also anti-clockwise, isn't it? So 1 times 4, so I'm putting that under the anti-clockwise moments, and I'm putting a tick because I've dealt with that force. This 5 Newton force, finger on there, push up here, and I've got that's going this way. Now that now is clockwise, so that's 5 times 2. So 5 times 2. I said 5 times 2 and wrote 1. There we go. So there's a 10 Newton meter force clockwise. There is 3 and 4, so that is 7 Newton meter force anti-clockwise. So what's the resultant force? Well, 10 Newton meters turning it clockwise, 7 Newton meters turning it anti-clockwise. So 10 take away 7 is 3 Newton meters clockwise. Okay, so that's the kind of thing that we're dealing with in this next section. I'm going to deal with a tricky little conceptual point, and then I'll do example 4. This point here, we're asking for the moments about this point. Now, it's easy to picture that as what I've been doing. I've put my finger on that, I keep that still, and then the whole thing's going to turn around that point. Now, actually, the way to think about it is that we don't actually have to have that point fixed and everything moving around that. Imagine it as these 3 forces are happening on this piece of paper. That one's pushing that way, that one's pushing that way, and that one's pushing that way. If I did fix that point, then what would happen is that it would be moving clockwise, because there's a total moment of 3 Newton meters clockwise. But if instead of putting my finger there, I put my finger here and kept it still here, but I kept these 3 forces going, then maybe something different would happen. That would push up, that would put down, that would push that way. Okay, so what we're saying is, if we put the finger there, then there would be a total moment of 3 Newton meters. If I put my finger here, then there might be a different total moment, and we'd say the moments about this point are such and such. Okay, now I can calculate that, the moment about this point, I can calculate the moment about this point, I can calculate the moment about this point, if I think about it as if I put my finger there, if that was the pivot point, if that was the bit that was going to stay still. I'm not actually saying that there is a pivot point there. I'm not saying anybody is holding that part of the paper still. I'm saying, right, if you had these three forces, what would happen? So the three forces are happening. What would happen if I kept that bit still? What would happen if I kept that bit still? Okay? So later on, there are questions where we might want to take moments about one point and take moments about another point, and the confusion comes because we think, well, if we're taking moments about that point stays still and everything turns around it. How can this system be turning around one point and turning around a different point? Well, it's not turning around those points. It's if you kept that one still, how would it turn? If you kept the other one still, how would it turn? So you can have, in one question, you might end up taking moments about point A and taking moments about point B, and then comparing the equations that you get, and that's why you can do that. It's not having to rotate about those 2 points separately. So right from the first example of this kind of thing, I just want to make that bit clear. If I put my finger there and had it as a pivot point, that is the way it would turn. That's not the same as saying it is actually a pivot point. So on this same question, I could say, okay, you found those moments, now find moments about a point over here. All right? So I'm going to do example 4 now, which looks like this. We've got P here, which is the point that we're taking moments about, so the point we're imagining to be fixed, or we're considering the consequences of what would happen if we did fix that point. And the forces that I have are 5 newtons there, 6 newtons here, and 4 newtons in this direction. This is at a 40-degree angle. This is at an 80-degree angle. Oh, sorry, my angles are a little bit out there, aren't they? My 40 degrees is almost as big as my 80 degrees. Never mind. I'm sure you can still picture it. And 1 meter. Okay, so we have clockwise forces. We have anti-clockwise forces. Sorry, I'm just going to change that. I like to put my clockwise forces and then anti-clockwise forces. I'll end up with them in the wrong places otherwise. Okay, I'm going to start with the easy one, the one that is at 90 degrees already. Put my finger on here and I push in that direction. Which way does it go? It goes this way. That is anti-clockwise, so 3 times 6 goes on the anti-clockwise side of things. This force over here, I'm pushing in that direction. Well, that's pushing clockwise. So that is 2 ways of thinking about it. One is to draw this line in here and say, is that distance times 4 newtons? So 4 newtons times that distance. What's that distance? Well, that is, here's my right angle triangle. The D is opposite the 40 degrees and the hypotenuse is 3. So 3 opposite means sine 40 degrees. So that's one way of doing it. The other way of doing it is to think of it as that 4 newtons can be split up into this component and this component. This component here, I'm just going to draw it over here because it will make my right angle triangle easier to see. In this right angle triangle, 4 newtons, this is the side that I want, is opposite the 40 degrees, so sine 40 degrees times 4, and that's at a distance of 3 meters away. So 3 meters times sine of 40 degrees times 4. So 4 times 3, sine of 40 either way. Over here, one way of finding the moment from this, this force here, put your finger there, push it in that direction, and we're going this way, which is clockwise. So whatever the moment is, it's going to come up over here. I've extended the line of the force, and I've drawn in a line at 90 degrees. So here is my right angle triangle. So I do 5 newtons, I don't need to put the n in the equation, times this distance here, and that distance is, well, this is 4, D is opposite the 80 degrees, so 4 sine 80, I've picked sine because it's opposite 80 degrees. If you want to, then do, sine 80 equals D over 4, and rearrange that, and you'll get that D equals 4 sine 80. The other way of thinking about it is like this. This 5 Newton force here can be thought of as that component there and this component here. In fact, I'm not going to move the component, I'll just leave it there for the moment. So what do we get? We get that these 2 component forces make that 5 Newton force. This component force I can ignore because it's actually acting down here, isn't it, through the line that involves a P. This thing here then is 10 degrees. So I get a distance of 4, and I want this force here in this right angle triangle. So that is 5 cos 10, because this is adjacent to the 10, times 5 cos 10 degrees. Now you might look at those two and say, hang on, they're supposed to be the same. That's the same moment calculated different ways, but of course sine 80 degrees is the same as cos of 10 degrees. And if you're not happy with that, then, well, if that's 10 degrees, this is 80 degrees over here, so 5 newtons sine of 80 degrees. Okay, so that's how we do those kinds of questions. Example 5 is just the same thing. It looks a bit different, but you put your pen there, push in that direction, and you'd make a clockwise moment. Put your pencil there, push in that direction, you make a anti-clockwise moment. So same techniques. Again, exercise 4A and 4B are worth a lot of practice. If you get those under your belt, then the idea of moments shouldn't be too bad for the rest of the book.